All right. Well, I thank the organizers for the opportunity to speak. So today I will talk about singular values of tensors. So the main goal is to show like how one way of generalizing the notion of singular values of a matrix to higher order tensors. So let me first talk a little bit about tensors in general. So we have a bunch of vector spaces. So if you want up to VD, and now we can take the tensor product of all these spaces. Now with a simple tensor, I mean just a tensor product of vectors. And we of course know that not every tensor is a simple tensor, but every tensor can be written as a sum of simple tensors. And so now we can define the rank of a tensor as the smallest r, such that this tensor can be written as a sum of r simple tensors.
Quick question. So the notation in parentheses.
Oh, that's just an index.
Just an index.
Yeah, because sometimes you get a lot of indices and then. Okay. So this notion of tensor rank actually generalizes the notion of rank of a matrix if you take d is equal to 2, right? Because every rank R matrix is the sum of R rank 1 matrices.
So T is the tensor, capital T.
Yeah.
Okay.
So rank of a tensor T. Yeah.
Okay.
So here's one of the reasons I'm interested in tensors. Namely, there's one very specific tensor, which I'll call the matrix multiplication tensor. It's sort of like if you do matrix multiplication, it's a bilinear map, and you can write it as a tensor, then you get basically this tensor. If you look at it, it's clear that the rank is at most d cubed, because that's how I wrote it. So here fn times n, that's the set of n by n matrices, and then this eij, they form a basis, just the obvious basis that you would choose. Now there's a result of Strassen that says that if the rank of this tensor is S, then you can show that then you can show something about the complexity of matrix multiplication. So here with complexity, I mean arithmetic complexity, so just addition, multiplication, subtraction, they all have cost 1, regardless of how big those expressions may be. So F here is any field. Now we know that the matrix multiplication with the usual method will take about n cubed multiplications, n cubed additions. But it turns out that Strassen already found that for d is 2, instead of rank 8, this tensor has rank at most 7. We know actually it's exactly 7. But so that shows that the complexity of matrix multiplication is actually O n to the power 2.81 rather than n cubed. So this is sort of the fast matrix multiplication that if you work with very large matrices, it actually gives you faster algorithm than our usual matrix multiplication. That result has been improved many times. It sort of seems to converge, but anyway, the best result now is something like n to the power 2.373 by Legal. Those are sort of more theoretical. They are not in practice. The matrices that we deal with aren't big enough for it to pay off. So sometimes this tensor decomposition, also known as the canonical Polyadic decomposition, and also comes with different names. So people in different disciplines have sort of reinvented these things and given it different names. So there are applications in psychometrics, and I don't know, they gave it the name And anyway, so this decomposition for which this R is minimum, so for which R is the rank of the tensor, that we call a CP decomposition, for short.
Oh, by the way, is it okay I ask a question?
Sure.
So for that matrix multiplication algorithm based on the
Yeah.
rank estimate, how practical is that algorithm? Is that procedure that does it tell you what the algorithm is actually, or it just tells you what the complexity is?
Yeah. So if you have an explicit composition of the tensor, it will actually give you a very concrete algorithm.
But just a bound that you mentioned that on the rank.
If you just know a bound on the rank, then that will not give you a practical algorithm. But if you have the explicit decomposition into this rank R decomposition, or rank S on that slide, I think, then that will give you an explicit algorithm.
So that 2.87, something like that, from the slide before, was it an actual algorithm?
Yes, it's very explicit. That I don't know the formulas by heart, but they're not too complicated. And so it's sort of like what you do is like you do for 2 to the power n times 2 to the power n matrices, and then you divide it up into big blocks and then you do some computations with these blocks, and then sort of inductively. So.
And does it carry a large constant, or the constant is around 1?
No, it's. Yeah, I can't really say exactly. I don't know what exactly the constant is. But for very large matrices, it does give you some speed up. So it is. It is implemented in some software. Okay, so the CP decomposition. Well, the nice thing about it is that it sometimes is unique. If for matrices, if you have a rank R matrix, it's typically not a unique sum of R rank 1 matrices. So there are many different ways of writing it as a sum of rank 1 matrices. But for tensors, it's somewhat nicer because often it's unique, but it's not always unique.
Any probability?
What was the question?
What's the probability of it having a unique decomposition?
Well, I wouldn't say that the generic tensor is unique, I'm not sure about that, but I do know, like, if you fix the rank, and then, like, a rank that's not too large, and then you write it as a sum of random simple tensors, then the decomposition would be unique. So, yeah. Yeah. So the decomposition is not very numerically stable. That kind of means, like, well, we'll see an example of that. But even though t might be small, these in the smallest rank R decomposition, these v's might go to infinity or might get very large.
Do you have examples of that?
Yeah, I'll get to an example later on. And well, another thing is that this CP decomposition can be difficult to compute. Like it's very easy to find the rank of a matrix, but finding the rank of a tensor is actually quite hard. Right? Otherwise, that problem of matrix multiplication would be much easier.
When you talk about a simple tensor,
Yeah.
You include the coefficient?
Yes.
Okay.
Like we can just, if you have a coefficient, we can sort of include it in one of the vectors.
Okay.
Yeah, you can just scale one of the vectors by the coefficient. Okay, so the many applications in applied math. So one of the applications in psychometrics. Well, there's a whole bunch of. I won't have time to go into that.
What is this psychometrics?
Well, it's sort of like in psychology that you sort of measure things like intelligence tests or things like that, or personality tests. Yeah.
And it has a lot of data to process. Is that what it is?
Yeah. So I think he started doing this like many decades ago. So at that time, I don't think they had like big data, but anyway, the data had sort of a kind of structure for which the CPU decomposition makes sense. Okay. So one thing one can actually also do is, like for these practical applications, you typically will have noise, so you might also have an error term. So then you can ask, maybe you fix the rank, but you want to find a rank R approximation that's sort of closest to the tensor that you're dealing with. So here's sort of one example that shows that sometimes there is not a best rank R approximation. So if you take this particular tensor, this t, then you can write it as a sum of two simple tensors, v1t and v2t. So it depends on the parameter t. So then t is v1 plus v2t plus a small error term. And as t goes to 0, then this error term goes to 0. So that means this t can be approximated by rank 2 tensors. And you can get arbitrarily close. However, this tensor itself is not rank 2, so you cannot write it as a sum of two rank 2 tensors. So that means there's not really a best rank 2 approximation of this tensor t. So that's kind of a thing that's not so nice. So I will use a little bit slightly different approach. So I'm going to replace the rank of a tensor by something else called the nuclear norm. And the idea of that comes from compressed sensing. So there's something they do there that's called convex relaxation. So there you may have a system of equations, but that's maybe underdetermined, so we have fewer equations than variables. So in principle, there are infinitely many solutions, but we want to find sort of a sparse solution, meaning that the solution has many zeros. So the sparsity of a vector can be measured by this, some people call it the L0 norm. It's not really a norm, but you can just count the number of indices for which the coordinate is non-zero. But that function, this so-called L0 norm, is not a convex function. So it's difficult to work with in practice. So a way to deal with this is instead of using this so-called L0 norm, replace it by the L1 norm. So L1 norm is just the sum of the absolute values of the coordinates. And that is a convex function, and it's actually a norm. And what turns out is that if you replace it, it turns out that you, in many situations, you might still find the sort of sparsest solution, even though you replaced this measure, this L0 norm, by the L1 norm. So there's some results by Candes, Tao, and Donoho that show that if, for example, this A is random in a certain way, with certain parameters, then the probability that you find a sparse solution with this method is close to 1. So there's some. So in some sense, if for random matrices, it might actually work. And so finding this optimization problem is now a convex optimization problem. So it's fast in practice.
Why x1? Why not say x2?
Why? Yeah,
It's linear programming, not quadratic programming.
yeah, but if you take the L2 norm, then it's no longer true that you find sort of the sparsest solution. So then you're basically doing these squares, and it has to do with sort of the geometry of the L1 sphere. Yeah, so yeah. You could perhaps do L1.5, might still work, but L1 in some sense the best because the sphere for the L1 norm is sort of the convex whole of all sort of sparse factors. Anyway. Okay. So for tensor, instead of working with the rank, we can also work with the nuclear norm. So the nuclear norm is the smallest value. So instead of trying to minimize R, we try to write T as a sum of simple tensors, but we minimize the sum of the lengths of these vectors. So this norm there is just the Euclidean norm there.
And
So-
so,
so
does not longer have error term, right?
Sorry?
No error.
No error term.
So these results later on, they only work for the real and not for any norm space.
Many of the things will also work over the complex numbers.
How about space that are symbolic and with some norm? I mean, operators, for example, have norms, right?
Yeah,
So if the vectors are vectors of operators, would these results work or not?
yeah, I'm not sure. Another norm for tensors is the spectral norm. So this number that I defined there is actually a norm, the smallest value of this sum, and it's actually well defined. The spectral norm is so if you take the smallest, the largest possible value of the inner product of this tensor with a simple tensor that has length 1. You can also think of this t as a multilinear function, and you're trying to optimize the absolute value of t over a product of these spheres, because all these components of V lie on the unit sphere. Now, these two norms, the spectral norm and the nuclear norm, are dual in the following sense that we always have this inequality. So the inner product of t and s is always less equal than the product of these two norms. That's the nuclear norm of t and the spectral norm of s. And for every t, there's an s for which we have equality and vice versa. So maybe I'll just mention here, like if we work with matrices, then for one thing, the rank I already mentioned, the tensor rank is the same as the matrix rank in that case. And the nuclear norm in that case is also the nuclear norm as it is defined for matrices, which is the sum of the singular values of a matrix. And the spectral norm is actually also the spectral norm or operator norm of a matrix. So that just as a map from one normed space to another normed space has an operator norm, and that's the spectral norm. And the Euclidean norm, which is sometimes also called the Frobenius norms for matrices, is just the square root of the squares of the singular values. So here's sort of an example that a particular tensor that I'm also interested in, namely the determinant. So the determinant, you can think of it as a multilinear function, and so then you can also think of it as a tensor. And so the tensor you get is this dn that I defined here. And it's clear that the nuclear norm is at most n factorial. Just the way I've written it, as n factorial terms. And also clear is that the rank is less or equal than n factorial. Now the spectral norm, if you write down what it actually means, then it means that you take the maximum of the determinant of this n tuple of vectors, where each of these vectors have unit length. And so there's a theorem of Hadamard that says that this maximum is 1. It's obvious, like for the square, the square is sort of optimal for the area for all parallelograms, right? So anyway. So then, from this inequality that on the previous slide, we see now that the nuclear norm is then greater equal than the inner product of dn with itself, which is the square of the Euclidean norm, which is easy to see is equal to n factorial. So that shows that the nuclear norm is at least n factorial. So the corollary is that the nuclear norm is n factorial. Now if we change the example a little bit and forget about the sign, then we get the permanent tensor. So the permanent tensor has a similar expression. Now the spectral norm is, you have to look at the maximum permanent of n vectors. So you put them together in a matrix. Well, you get maximum permanent if all these vectors, or if this whole matrix all have the same entries, namely 1 over square root n. And so that's a theorem by these 3 people. So the maximum is n factorial over n to the power n over 2. That's exactly when all these VI's are all the same. And all, yeah. So doing a similar calculation, it shows that the nuclear norm is at least n to the power n over 2, so we get a weaker lower bound for the nuclear norm of this permanent tensor. But actually there's an interesting formula by Glynn for the permanent tensor that's, well, here's the formula. It's a sum over 2 to the power n minus 1 terms. So we see from this already that the rank of this permanent is not n factorial, but actually much less, namely at most 2 to the power n minus 1. But it also shows that if you do the calculations, it shows that the nuclear norm is at most n to the power n over 2. We also have a lower bound, but I may not talk about it. But the lower bound kind of shows that we're actually not too far apart from the lower bound, right? The lower bound is, anyway, yeah, something like 2 to the power n over square root n. So in this case, we also know the nuclear norm of this permanent tensor, but interestingly, it's different than for the determinant tensor.
So for determinant is what, n factorial?
Yeah.
So permanent's bigger.
The nuclear norm is smaller. Yeah. The nuclear norm is smaller for the permanent. But the spectral norm is bigger.
But how is it calculated to the fact that permanent is easier to compute than, or is orthogonal to that fact?
Yeah.
Or permanent is hard
For these, the computational complexity of computing determinant and permanent for these bigger tensors don't really relate to the rank of these tensors.
Okay.
So permanent is actually more difficult to compute than the determinant.
Right, yeah,
Yeah.
there's no polynomial time.
Right.
Okay.
Or at least I should say conjecturally it's more difficult. right? It's like P is NP. Anyway, yeah, so we again try to minimize the sum of the lengths for a tensor. Let's see. So again, if we now we can look at this nuclear norm, but now we can also add in the error term. So then we can write T as a sum of some number of rank 1 tensors plus an error term, and maybe we can fix sort of the nuclear norm, like fix the sum of the lengths of these vectors, of these simple tensors, and then try to minimize the error. So in some sense, same as we did before, we fixed the rank R and then find the best rank R approximation. So now we can also fix the nuclear norm and find the best approximation with that given norm. And it's sort of nicer because that problem always has a unique solution. So this approximation will be unique, but maybe its decomposition may not be unique. Decomposition in rank 1 tensors. So what you get is some kind of optimization problem. There are different ways of formulating it. So you could, for example, limit the nuclear norm, or you could maybe limit the error and then try to minimize the sum of these lengths. So there are various ways of writing down optimization problems that will give you these kinds of decompositions. Okay, so now I'm going to work towards the generalization of singular value decomposition. So for that, I need following definition. So again, this V1 up to VR, these are simple tensors. And let's say they also have unit length. And so now make the following definition. We say that these simple tensors are t-orthogonal if the following inequality is satisfied for every simple unit tensor of W. That's kind of, yeah. So, if you think about it, if you take for example t is equal to 1, like if the VI's are orthogonal, then this is just the Pythagoras theorem, right? It's equal to 1 in that case. Or, well, it follows from Pythagoras theorem. But if t is smaller, then the inequality becomes, if t is larger, then the inequality becomes stronger. So one orthogonal in this definition is equivalent to just being orthogonal. So if t is larger than s, then t orthogonal implies s orthogonal. So we get stronger notions of orthogonality. There's also a result that you cannot have too many orthogonals in a sense. Like if V1 up to VR are unit tensors that are t-orthogonal, then the number of them cannot be more than the dimension of the whole space to the power 1 over t. So obviously for t is 1, it's just the dimension of the space. But if, for example, you have two orthogonal tensors, then you can only have the square root of the dimension. Some other properties of this notion is if you have vectors or unit tensors that are t-orthogonal and simple tensors that are s-orthogonal, then if you take tensor products, they will be s plus t orthogonal. So that's a nice property. Then there's also something what I call vertical tensor product. So if you have a vector space that's a tensor product of these spaces, and another vector space is also a tensor product of these spaces, then we can form the tensor product, but we can group V1 together with W1 and so on. So again, this tensor product of V and W, we think of it as a tensor product of these spaces again. So I use this sort of box tensor notation for that. Similar, if you have a simple tensor, then we can, and in V and a simple tensor in W, then we can form this tensor product. And we view it in this V box tensor W there. So maybe you can think of it as if you have two matrices, then you can take the tensor product and you can view it as a tensor product of four spaces, or you can think of it again as a linear map from one tensor product space to another tensor product space. And so then it's sort of just a two-way tensor.
So they're just alternative ways of breaking up that tensor?
Yeah.
They're equivalent in some sense?
Yeah, so things do depend on how you view it, right? So, for example, if you have a tensor product of three spaces, sometimes what people do is group two together. We call it flattening. Then you just get a matrix. And sometimes you can compare the matrix with the tensor and so on. So there are different ways of grouping spaces together. Another result is for this vertical tensor product. So if I have a bunch of unit tensors, simple tensors in V that are t-orthogonal, and I have simple tensors in W that are t-orthogonal, then this, if I take this vertical tensor product of all these, so of all pairs, then those will be t-orthogonal again. So the construction is slightly different because there I had R and R and produced R, and here I have RS and now produce RS new tensors. So now I can define what I call the diagonal singular value decomposition. So an expression T is sum lambda I Vi is called a diagonal singular value decomposition if while the lambdas are, say, positive and we can order them. The VI's are two orthogonal simple tensors of unit length. So in this case, I take the coefficient out. So then I call this a diagonal singular value decomposition. Now I should warn that this diagonal singular value decomposition doesn't always exist for all tensors, so that's bad. But when it does exist, it has all kinds of nice properties. In particular, if for these two, then we are in the matrix case, then this corresponds to the usual singular value decomposition of a matrix. And the lambda i's are just the singular values. There are other generalizations of singular value decomposition, but in some sense they're very different. They have perhaps other nice properties, but they don't really generalize the CP decomposition. They're not really closely related to that. So this is sort of closer related to CP decompositions, right? Anyway. So the nice thing is that if a tensor has a diagonal singular value decomposition, well, these lambda i's were called the singular values, and these have exactly the same properties as for matrix singular value decompositions. So this nuclear norm that we defined is the sum of the singular values that we defined. And same spectral norm is again the largest singular value, and so on. So it's all compatible. Also, the nice thing here is that if the singular values are distinct, then the diagonal singular value decomposition is unique. Yeah, I think that's also true for matrices. But here's another result that is not true for matrices, or well, it doesn't make sense for matrices. If these simple tensors are t-orthogonal and t is strictly larger than 2, then this diagonal single value decomposition is unique, even if the single values may be the same. So if you have a matrix where the single values are all the same, then the single value decomposition may not be unique. So now we get back to this example of matrix multiplication. So if you just choose a basis of Cn, then they are orthogonal. So now, using this one property, if I take the tensor products with itself for all these vectors, then I get something that's 2 orthogonal. So that's sort of the horizontal tensor product property. Oops, wrong button. So now I can look at these and group them together different ways. So here, the first one I view it as a tensor Cn, tensor C, and so then I do it several different ways. But now I can take what I called the vertical tensor product of all these sequences of tensors. And what I get is basically the set of these tensors. So now I have n-cubed tensors that are 2 orthogonal. Okay, and now we can think of this EI tensor EJ as EIJ. And so that shows that all these tensors, that shows that this expression here, well, I think I called it Mn before, but anyway, that this tensor, so these terms are 2 orthogonal, so this expression is a diagonal singular value decomposition. And so the singular values of this tensor are just ones. So you have n cubed. So a singular value 1 with multiplicity n cubed. In particular, we see that the nuclear norm is n cubed. So maybe that's disappointing in the sense that somehow the usual decomposition for this tensor is actually optimal for the nuclear norm. But we saw the other example of this permanent, that the usual decomposition, that if you try to minimize this this nuclear norm, that you actually get a very low rank decomposition of the tensor. So the heuristic is that if we try to minimize this nuclear norm, that we would get a low rank decomposition, but we won't always get the lowest possible rank. Here's another interesting algebraic example. If you have a group, then we can look at sort of the group multiplication, and that gives us a certain tensor. So we can look at the group algebra, which is a vector space, and then we can consider the following tensor. If this tensor, if the group is z modulo nz, then this tensor tells you basically how to multiply polynomials. And it's related to discrete Fourier transform in that case. So here's the result, that this particular tensor always has a diagonal singular value decomposition. And the singular values are as follows. Well, you have to look at the dimension of the irreducible representations of G. And, well, then these are the singular values. So n over square root di appears with multiplicity di cubed. And the sum of the cubes is then an upper bound for the rank. But probably better because we know that we have this result of Strassen. Okay, so again, finding this lowest nuclear norm decomposition will actually tell you something about the structure of this tensor in this case. So here's a little argument that shows that this permanent tensor actually doesn't have a diagonal singular value decomposition. Basically, maybe I'll skip quickly over it, but basically it's because you could actually calculate what the multiplicity would have to be, and it's not an integer. So although we know a lot about this permanent tensor, we know its nuclear norm and spectral norm, but it will not have a diagonal single value decomposition. Okay. So unfortunately, not every tensor has a diagonal singular value decomposition, but we can still say something even if tensors don't have this diagonal singular value decomposition. So we can sort of still define singular values or something like it, or at least a singular spectrum. To do that, I place it sort of in a more general context of signal denoising. So think of it as A as some signal, B as some additive noise, and then C is the sum, which is a corrupted signal. Now, typically, original signals are typically sparse in some sense. Noise is typically small with, like if it's Gaussian norm, it's typically small with relation to some L2 type norm, or maybe Euclidean norm. So, in particular, the case that we looked at earlier is where one norm is maybe a nuclear norm, and the other norm is maybe L2 norm. So, for low-rank tensor with noise, the noisy part will have low Euclidean norm, and the low-rank part will have low nuclear norm. So there's sort of this general context where we have a vector space, let's say finite dimensional, and we have two norms on this vector space, say norm x and norm y. And then we can try to do the following. We have some vector c, and we want to decompose it as a plus b, where a has a small norm with respect to x. So there should have been an index x here and an index y. Sorry about that. So a has small norm with respect to x, and b has small norm with respect to the y norm. And we're looking for optimal solutions. So we say that this pair of values x, y is Pareto optimal if it has the following properties. Whenever we have another decomposition, then either the x norm of A is bigger or the y norm of B is bigger. So we try to minimize the x norm of A and the y norm of B at the same time. And these are competing objectives. And we can look at the trade-off. And so we can graph this trade-off. So then we get some function. Let's see if I have okay. Sorry, I don't have a picture. But it's just some function that's decreasing. So for every value of x, you can sort of look at the optimal value for y. Now it's particularly interesting. I should also point out, like if we have such an optimal decomposition that's Pareto efficient, then we call it an XY decomposition. And this graph that shows the trade-off between the x norm of A and the y norm of B is called the Pareto Frontier. Now the special case is when one of the norms let's say that we have two norms x, y that are dual to each other, And on top of that, we also always have the Euclidean norm. So then now we have 3 norms on the vector space. Now we have the following result, that the following 3 statements are equivalent. So C is A plus B is an x2 decomposition. So that's where we try to optimize the x norm of A versus the L2 norm of B. That's equivalent to saying that C is A plus B is a 2y decomposition. So that's when we try to optimize the 2 norm of A versus the y norm of B. And this is also equivalent to this inner product of A and B being equal to the product of these norms. So remember, these norms are assumed to be dual to each other. So we always have less or equal, but 3 says that we have equality. So now I define the Pareto subfrontier. So I look at all these x2 decompositions, which are the same as 2y decompositions, and I plot the x norm of A versus the y norm of B. So it's a slightly different optimization problem, but what I plot is something different. So I sort of still plot the x norm of A versus the y norm of B. So this Pareto subfrontier is also a nice function that's continuous and strictly decreasing. It may not necessarily be convex like the Pareto frontier. Now, in some cases, the Pareto frontier and the Pareto subfrontier might be the same. In that case, I call the C, I call it tight. And if all vectors are tight, then I call the norms to be tight. So let me just do an example here. So this is a simple example where I have, I take 2-dimensional space. I take 2 norms, and these 2 norms are actually dual to each other. And I take some vector, some random vector here, and now I can look at all so-called x2 decompositions and then plot the x norm of A versus the y norm of B. You get this blue graph. So the blue graph here is the Pareto subfrontier, and the green graph is the Pareto frontier. So in this case they're not equal, so this C is not tight. From the definitions, it's clear that the frontier is always below the subfrontier, or equal. But if they're the same, it's very special, then we call this vector tight. The subfrontier is nice because this graph tells us basically everything about all the norms. So if you take a point on this graph, that means that we have a decomposition, C is A plus B, for which the x norm of A is this, given by this point, and the y norm of B. Then the area under the whole graph turns out to be exactly half times the square of the Euclidean norm. And like if you take the area of this part here, then you get half times the square of the Euclidean norm of B, and so on. So the x norm of C is where this graph ends, and so on. So you can sort of see all these norms somehow in this picture. Now this general framework applies to a lot of situations. For example, I just mentioned one here, like image denoising. So there's this method of total variation, image denoising, that fits into this framework. There the norms are not tight. If you do it for 1-dimensional signals, then it turns out these norms are tight, which gives you very nice properties. Anyway. So I already talked about singular value decompositions and these norms. But I just want to point out in that situation where we can take for this one norm to be the nuclear norm, the other norm, the dual norm, is then the spectral norm. And in this situation, these norms are tied. So that has particularly nice consequences. Now, if we look at the singular value decomposition of a matrix, then we have a description of the Pareto Frontier, which is the same as the Pareto subfrontier. So it's some piecewise linear function that's determined by the singular values. So that means that if I have this graph of this Pareto Frontier, then from that I can deduce what the singular values are. So the whole point here is that this Pareto Frontier encodes the same information as the singular values of the matrix in this case. So this now allows me to generalize things to tensors, because this Pareto Frontier I can also define for any tensors, or this Pareto subfrontier. And so I could use the same procedure to define what the singular values are for those tensors. There are some special decompositions. So if you have a vector that's tied in this context, which could be a tensor, if you work in the context of tensors, but so in this general context, there's some kind of decomposition that's somewhat similar to a singular value decomposition, and I call it the slope decomposition. So it's some decomposition at certain properties with respect to these norms. It turns out that if a vector is tied, then a vector is tied if and only if it has such a slope decomposition. In the example of a tensor that has a diagonal singular value decomposition, from that you can also deduce a slope decomposition. But the slope decomposition can actually be defined more generally. So even in the case of tensors, even some tensors may not have a diagonal singular value decomposition, but they might still have a slope decomposition. It's quite nice, it's unique if it exists. And if you have slope decomposition, from the slope decomposition you can define singular values with multiplicities. Now the multiplicities here may not necessarily be integers, okay? But you have a discrete set of singular values and they have multiplicities. But for example, for tensors, if a tensor has diagonal singular value decomposition, then these multiplicities will have to be integers, and then exactly as the singular values that we defined before. So it's sort of compatible with that definition. So even though the multiplicities may not be integers, we still have these results in the general context that if some general context where these two norms are dual to each other, so the X norm can be written as the sum of the multiplicities times the singular values, even though the multiplicities might not be integers. The Y norm is the largest singular value, and similar formula for the Euclidean norm. So, like I said, a particular interesting application is tensors. So one norm, the X norm, is say the nuclear norm. The Y norm, we take the spectral norm. And if you have a diagonal singular value decomposition that we defined before, then that sort of coincides. Now the permanent, as we saw, doesn't have a diagonal single value decomposition, but with this sort of more general, in this more general context, we can still define a singular value and the multiplicity. And turns out it has this particular singular value with this particular multiplicity. So in that case, this tensor Pn is tight, but even if a tensor is not tight, we can define, we still have a Pareto subfrontier and can still use that to define some singular spectrum. So here's an example that we looked at before. This particular tensor was this tensor that has rank 3, but can be approximated arbitrarily close with rank 2 tensors. So I was actually able to compute the Pareto Frontier and Pareto subfrontier in this case. And so using the definition, we get the following singular spectrum. So now we see that it's not like singular values with multiplicities, but are also, well, it's sort of continuous now, right, in some parts. So that means that some singular values, I guess you could say, have infinitesimal multiplicity. It's quite curious. So it turns out that the spectral norm, which is the height, right, of this graph, is 2 over square root 3. That's the spectral norm in this case. So the nuclear norm should be, well, usually it's the sum of the singular values, but if you have a graph like that, it's just the area, right? So the area is the nuclear norm, and in this case, it's equal to 3. And if you think of this as a function of the graph, then to get the L2 norm, or the square of the L2 norm, you have to integrate the square of the function. Or equivalently, you could integrate 2y over this whole region. Then you get, again, the value 3, which is the square of the Euclidean norm. So again, basically this picture tells you again all the norms of the tensor. And yeah, it tells you basically how well you can approximate this particular tensor with tensors of a given nuclear norm. So maybe I'll end here.
Thank you.
So, as far as I understand, people use singular value decomposition for matrices for approximation, right? You can construct SVD and throw away part corresponding to singular values, small singular values.
Yeah.
So, if I have this like implicit SVD, can I use that for approximation?
Yes. So yeah, there's this method, principal component analysis,
Yes.
right, where they throw away the large singular values. And yes, that's exactly the way we defined these. Essentially, that's how we defined the singular values here this way, right? We're looking at how well you can approximate things.
So you take and like the point on this frontier is approximation.
It's slightly different, I guess, because they're like a principal component analysis. You fix the rank and then you find the best rank R approximation. And as we see, that doesn't really work well for tensors. So we replace it by the nuclear norm. But you could do the same thing for principal component analysis. You get a slightly different answer. So in some sense, this principal component analysis is sort of what I would call hard thresholding. And this is sort of more short thresholding. So you would throw away the smallest singular values, but maybe also slightly decrease the larger singular values. So if you, yeah.
And I have also follow-up question. So because and I think another application scenario for usual SVD is that you look actually on these simple tensors. So like these vectors, they have some physical meaning.
Mm-hmm.
So, but in this case, I cannot can I somehow read off some simple tensors that would approximate me well, or something like that? Does this make sense?
Yes.
So this principal component. What are actually these principal components? Somehow.
Yeah. So for general tensors, yeah. So if you have this diagonal singular value decomposition, then we really have this like decomposition.
Yes. Then,
So for general tensors, we may not have that. But I also feel like there's some reasons why you cannot have that some way, like in general. Yeah, so like for example, the nuclear norm may not, or this nuclear decomposition might not be unique, and there may be many different ways of decomposing.
yes.
It's kind of hard to explain, but some things are really different for tensors. Yeah, so it's for some applications, depending on where the data comes from, there might actually be a nice decomposition into rank 1 tensors, but in other examples there might not be really sort of any natural decomposition. So
it depends on data, more or less.
yeah, but also like some of the tensors using groups, they may have a lot of symmetries. And then the strange thing is that the decompositions couldn't have all these symmetries. So it's kind of unnatural to write down some decomposition that doesn't have the same symmetries as the tensor that you started with. I don't know. Yes.
Different question. Your matrix tensor,
Mm-hmm.
do you have something similar? Can you do something similar for, say, the matrix multiplication for, tensor? Is that right? Is there something similar for zero-dimensional ideals? You have multiplication matrix there?
Yeah, but it's a matrix, right? It's not a tensor. It's sort of
Right. It is a matrix, right? It's a multiplication matrix.
no, but it's still so it is tensor. It is tensor because it's bilinear. Bilinear, yeah.
So is there a similar thing about the rank there?
Yeah, I think this is connected to what Harm showed about FFT. So there was a tensor that corresponded to the multiplication of polynomials modulo x to the n minus 1. So I think Harm will. Yeah, so this is in. So this tensor corresponds to multiplications modulo ideal of roots of unity.
Yes.
Then you can extend this to any zero-dimensional ideal.
I don't know, maybe Harm knows.
Yeah, I'm not so sure if I understand the question. Or
Well, you can set up multiplication matrices for zero-dimensional ideals, right?
yeah, so for any finite dimensional algebra, you can write down a multiplication tensor.
Yeah, that's what she's asking. So
Yeah.
what we can
But
make
there's
fast.
structure there, right? It comes from, it's defined by polynomial equations and things like that.
Like, people working in this algebraic complexity theory have studied like basically all kinds of algebras, particularly commutative algebras. So in the end, they usually reduce to matrix multiplication. They have results or how these things are related. Like if you have a simple, if you have a simple algebra, then it's just a or a semi-simple algebra, then it's just a product of matrix algebras over over complex numbers. But it gets, it's a little bit more general, yeah. But people have studied this. This multiplication in arbitrary algebras.
I wonder if that's related to whether these kind of optimization or approximation carry through from the tensor to the tensor algebra.
Uh-huh.
Is that something what you were asking?
I'm not sure. I don't think I'm not in that direction.
So suppose you have one tensor in one space and another in another,
Yeah.
and you approximate each one of them, and suppose you want to multiply the two tensors to in a higher dimension space together.
Yeah.
What would be the rules, let's say, between the three? So that would carry
Yeah.
through this into the tensor algebra itself.
Yeah. So, if I understand your question right, you could have two tensors in two different tensor product spaces,
Right.
and just take the tensor product of those,
Yeah, right.
and then wonder like how these things
how
are
these
related.
things- yeah, that's right.
Yeah. So the spectral and nuclear norm are sort of multiplicative, but what happens to the singular values, it's a little bit more complicated. So I haven't quite
So you
figured
could have
out.
optimized this one and optimized this one,
Yeah.
but together
Yeah.
you may have even a better one, or
Yeah, it's not quite clear like what. So we know something about all the approximation of one tensor and approximation of the other tensor.
right?
But then when you take the tensor product, it's not quite clear like what you approximate this tensor product by.
Yeah.
Like you have written one as a plus b and the other one as a prime plus b prime, and now we took the tensor product, and now we have to write this tensor product as sum of two things. But which two things would you choose? Because
Well,
we have no like four
we,
things.
we don't
now.
even know if the rank add or
Yeah.
right. Or they could be even have a smaller rank. I mean,
Right. Yes.
two,
The rank can
two,
go down.
Then
Yes.
you might go down, right?
Right. Yes.
So I think this is, I mean, to extend it to the tensor algebra, have something to do with what you're asking, because in the modular ideal kind of thing, that's a tensor algebra. No? Or am I wrong? Not just a tensor. I mean, you can
No, right.
multiply two polynomials together, right? Not the same ideal.
Yeah, that's a tensor.
Right. Well,
not
each one of them is a tensor, in a way. Well,
Well,
I mean,
in a way, yes,
it
but
depends on the level you're talking about.
Yeah, but when you model out the ideal, it doesn't make much sense to look at it as a tensor, right? Because it's now finite dimensional space, right? So
You think about it's finite dimensional.
yeah,
Oh, okay.
yeah. She was asking about two-dimensional ideals, yeah.
Mm.
So it's finite dimensional algebra, and in this case, maybe tensors is not that productive. So maybe if you go higher, then you have to think about it as tensors.
So in concrete applications that you mentioned, how finding that representation with the smallest r is helpful?
Well, there's maybe one application that I could try to explain. Sorry. Right. Thank you.
Would you mind writing on the other board?
Well, there's one application in from chemistry. It's a like imagine that you have like these are all kinds of solutions. These are sort of solutions.
Test tubes.
Yeah, these are test tubes, and we know there's some unknown compounds in each of these. They're the same compounds, but for each of the test tubes, for each of these samples, they are in different concentrations. And we actually don't know anything about it, right? But what one could do is do the following experiment. So one can use light at various frequencies, then this solution will emit light, but perhaps at different frequencies. So you sort of excite molecules with this light, and then you will emit light at certain frequencies, and each of these compounds will sort of react in a different way. And so basically now we have a bunch of frequencies here and a bunch of frequencies here where we can measure. And then we can do that for each of these test tubes, for each of these samples, so then you get a tensor. Now, this tensor we can then decompose. Okay. And now each of these simple tensors corresponds to one compound. So one vector will tell me like what the concentration is of this compound in each of the samples. This BI might say like how this compound absorbs the light, from which frequencies it gets the energy. And then the CI might say at what frequencies this particular compound tends to emit light. So now, if you have a tensor and we find this decomposition, then basically we get all this information at once.
I'm not sure. So you mentioned a few things that you assume are unknown.
Yeah, almost everything is unknown here. But the tensor decomposition gives you suddenly a lot of information. It doesn't tell you what exactly the compounds are, but for each summand you have some vector that tells you the concentrations, maybe up to a scalar, right? Because this decomposition is not completely unique in the sense that I can take a scalar and move it to another vector here. But anyway, it tells you the relative concentrations here. And for a certain compound, and then also this absorption spectrum and this spectrum of the light that it emits.
I'm just not getting the example.
So in each of the tubes, you have like the same compounds with different proportions.
That is one set of compounds.
Yeah,
A vector. You have a vector of
a common
numbers.
set of compounds,
Yes,
and they are mixed in the tubes, and you don't know the proportions. Right?
Okay.
Or, yes, but you
So
know.
it's AI.
Pardon? Yes, these are AI proportions. You don't know that.
Oh, unknown. Okay.
So, and also each of these compounds have some properties how it works with light. These are BIs and CIs. This is also unknown.
So everything is unknown.
But what is known is how each tube reacts with light.
Which is what?
Which is T. Which is tensor T. So T is I take T like ijk means I take ith cube, act on it with frequency j, and measure frequency k in the output. But this output itself is like a sum of the things that each compound in this tube does. And then you want somehow to to separate them. These effects.
I don't know if this makes it easier, but this tensor, I can think of it as a function in x, y, and z, right? So one is sort of the sample, which sample I'm considering, and maybe this is like the input frequency or the absorption frequency, and this is sort of the light that it emits with its frequency. So it's a function in 3 variables. And now the sort of underlying assumption is that this, like if there was only one compound, that this would be basically a function in x times a function in y times a function in z. Okay. But now, if you have several compounds, a mixture of compounds, then it will be a sum. It will just be linear. Okay. So now the nice thing about tensor decomposition is often it's unique. So if I start with a tensor and I find decomposition, then actually I find back these functions a, ai, bi, ci.
Thank you.
Can this be used for data compression?
Yes.
I think you mentioned it way in the first slide or something.
It generally, like if you have a tensor, right? And if the tensor is sort of assumed to be low rank, so it may have this plus some error, but basically, yeah, you could just store this information, and that would compress your data, right? So it's a way of dimension reduction, as to say, right? So if this R is small, then the number of dimensions here is much smaller than the number of dimensions there, right? Here's just R times the sum of these dimensions, and here's like a product of three things. So. Yeah.
Thanks, Victor, again.
Thank you.